Welcome to Algebra 2, Section 3.2, Apply Properties of Rational Exponents. You will see in this section that all the properties that we have applied to exponents also apply if the exponents are fractions. So, for example, when we multiply like bases, you might remember that we can do that by adding the exponents. So a to the m power times a to the n power is the same as taking a to the m plus n power. Well, what if we have fractional exponents? Maybe I have x to the 2/3 power times x to the 3/5 power. Well, I have like bases of x, and I can combine them by adding the exponents. So x to the 2/3 power plus 3/5 power. And then you have to remember that if we're adding fractions, we need a common denominator. Least common denominator here between 3 and 5 would be 15. So I'm looking at, let's see, 10/15 plus 9/15 would be 19/15. So this would equal x to the 19/15 power. The second property is raising a power to a power. You might remember when we raise a power to a power, we can do that by multiplying the exponents. So this would be the same as a to the m times n power. And again, this will also apply if our exponents are fractions. So if I had a to the 2/3 power, then raise that to the 9/10 power, well, I can simplify that by multiplying the exponents, 2/3 times 9/10. And then remember with multiplying exponents, we don't need a common denominator. We can just multiply numerator times numerator and denominator times denominator. But we also want to save ourselves a little bit of time in the process by cross-canceling if possible. So I'll look for common factors between 2 and 10. That would be 2 would be a common factor. So I could divide out the 2 from both and essentially cancel the 2's, leaving me with a 1 and a 5. And if I look at the other diagonal, they have a common factor of 3. So I can cancel out the 3, a factor of 3 from each, leave me with 1 and 3. So this will equal a to the 3/5 power. Next, we have a power of a product, and we can distribute the exponent to everything in the product, each factor, and write that as a to the m power times b to the m power. Now, sometimes it's going to be helpful to simplify going in this direction by distributing the exponent. Other times it's going to be helpful to simplify going in this direction by multiplying the bases if the exponent is the same. So an example of this with fractions, if I have 9 times 16 raised to the 1/2 power, well, both 9 and 16 are perfect squares. So it helps if I distribute the exponent, 9 to the 1/2 power times 16 to the 1/2 power. And I can quickly simplify this. The square root of 9 is 3. The square root of 16 is 4. And 3 times 4 is 12. Or going in the other direction, if I start out with 25 to the 1/3 power times 5 to the 1/3 power, well, the cubed root of 25 is not a whole number, and the cubed root of 5 is not a whole number, but they're both raised to the 1/3 power. So I can combine these by taking 25 times 5 raised to the 1/3 power, and if I multiply those together, I get 125 to the 1/3 power, which just equals 5, because 5 times 5 times 5 equals 125. We looked at an example with a negative fractional exponent in the previous section. And remember, with negative exponents, we need to move them to make them positive. So a to the negative m power would be the same as 1 over a to the positive n power. And again, with fractions, what that would look like, if I had 25 to the negative 1/2 power the first thing I want to do is rewrite it with a positive exponent. So I need to move it to the denominator to make the exponent positive. And then I can evaluate 25 to the 1/2 power, or the square root of 25 is just 5. So 25 to the negative 1/2 power equals 1/5. Now let's look at dividing like bases. You might remember when you divide like bases, the base stays the same, and we subtract the exponents. So a to the nth power divided by a to the nth power is the same as a to the m minus n power. Now let's look at that with some fractional exponents. If I had 3 to the 2/9 power divided by 3 to the 1/5 power, actually let's make it 1/6 power. I can combine those by leaving the base the same and subtracting the exponents. So 2/9 minus 1/6. Now to subtract fractions, just like adding fractions, I need a common denominator. And so I want the least common multiple of 9 and 6, which would be 18. So 2/9 would equal 4/18. And 1/6, let's see, I need to multiply that by 3, so that equals 3/18. And 4/18 minus 3/18 would be 1/18. So this would be 3 to the 1/18 power. And the sixth property is a power of a quotient, where we can distribute the exponent to everything on the numerator and everything on the denominator. Now, with distributing exponents, like in property 3 and property 6, we can only do that with multiplication and division. Do not try to do that with addition or subtraction. All right, let's look at an example of how we could use this. If I had 81/625 raised to the 1/4 power, well, first of all, 81 over 625, I can't reduce that any. But I can take 81 to the 1/4 power and 625 to the 1/4 power and simplify from there. The fourth root of 81 is 3, because 3 to the 4th power is 81. And the fourth root of 625 is 5. So that simplifies to 3/5. And again, with this property, sometimes it's going to be helpful going in this direction to simplify. Other times it's going to be helpful going in this direction to simplify. And we'll look at some more examples later. Now let's look at related properties of radicals. Since the nth root of a is the same as a to the 1/nth power, the properties that we were just looking at involving rational exponents apply to radicals as well. So if I take the nth root of a times b, that's the same as taking the nth root of a times the nth root of b. Essentially distributing the nth root to all the factors underneath the radical. Similar with division, if I take the nth root of a quotient, that's the same as taking the nth root of the numerator divided by the nth root of the denominator. And you can see how that is related to property 6 that we looked at previously. Now let's apply these properties to simplify some expressions involving radicals or rational exponents. I'm going to use the examples from the guided practice in section 3.2. First example says simplify the expression, and we have 5 to the 1/3 power times 7 to the 1/4 power, and that's being raised to the 3rd power. Now where I would start is looking at what's in the parentheses, and I see that I do not have like bases. I also do not have like exponents, so I really can't combine those. So what I'd want to do next is go ahead and distribute this exponent to both factors. And remember, power to power we multiply. So 5 to the 1/3 power and then cubed would be just 5 to the 1st power, since 1/3 times 3 is just 1. And then 7 to the 1/4 power cubed would be 7 to the 3/4 power, since 1/4 times 3 is 3/4. From there, if I'm simplifying, I still want to combine as much as possible, but once again, I don't have like bases, so there's nothing else I can combine and simplify, and that would be my answer. Next example, number 2 in the guided practice, is 2 to the 3/4 power times 2 to the 1/2 power. And I can see here I am multiplying like bases. So the base stays the same, and I add the exponents. So 3/4 power plus the 1/2 power, which I need a common denominator. So I want to change 1/2 to 2/4. And then adding the numerators, 3 plus 2 is 6, so I have 6/4. And that would reduce to 2 to the 3/2 power. Now, what you'll see, I'd prefer for you to leave your answer like this. Another way we could write it is splitting that up and seeing that we have 2 to 2/2 power, which will just be 2 times 2 to another 1/2 power. So split up that 3/2 into 2/2 plus 1/2, which is 3/2. And I could write this as 2 times 2 to the 1/2 power. Or 2 times the square root of 2 would be another way of writing that. Now, each of these is equivalent. This, if you can read it, that's 2 times 2 to the 1/2 power, 2 times the square root of 2 right there, and 2 to the 3/2 power. Those are 3 different ways of writing the same answer. I prefer that you just leave it like this, but you will see if you compare your answers with the back of the book as you're doing your homework. Sometimes they'll go ahead and change it to one of these other formats. Okay, example 3 in the guided practice. Hold on, let me get my pen up here. We have 3 divided by 3 to the 1/4 power. So here I'm dividing like bases, so I subtract the exponents. Now 3 would be the same as 3 to the 1st power. So I want to do 1 minus 1/4. Base stays the same, so I have that 3. 1 minus 1/4 would be 3/4. So my answer here, 3 to the 3/4 power. And because the numerator is smaller than the denominator, there's really no way I could split that up or simplify it. So I'll leave it like that. All right, next let's look at number 4 on the guided practice. For this one, we have 20 to the 1/2 power divided by 5 to the 1/2 power. And then all of that raised to the 3rd power. All right, now I'd start with, in the parentheses, 20 to the 1/2 power is not a whole number, so I can't simplify that. 5 to the 1/2 power, not a whole number, so I can't simplify that. And I could distribute the 3 first, but what I notice here is that they're both being raised to the 1/2 power. So what I could do with that is combine the 20 divided by 5 in parentheses, raised to the 1/2 power, and then cubed. So notice I just, instead of distributing the 1/2, I took it out of both the numerator and the denominator, but still equivalent to what I started out with. 20 divided by 5 is 4. And then I want to raise that to the 1/2 power and then cube it. And this will simplify nicely for us since the square root of 4 is 2. And then I can take 2 to the 3rd power, which is 8. So there we have it. When simplifying radicals, we not only want to combine as much as possible, we also want to take the nth root of any factors possible. What I mean by that is if we have the cubed root of, say, 54, well, the cubed root of 54 is not a whole number. But we can split this up into 27 times 2. 27 is a factor of 54 that is a perfect cube, meaning the cubed root of it is a whole number. So with this, I can take the cubed root of 27 times the cubed root of 2, and we've simplified radicals like this before. Just now we're going to look at beyond just square root, but cubed root, fourth root, etc. Cubed root of 27 is 3, and then the cubed root of 2 is not a whole number. So this radical in simplest form looks like this, 3 times the cubed root of 2. It's equivalent to what we started out with, but we took out as much as we could from underneath the radical sign. Another thing we want to look at when simplifying radicals is that we want to get rid of radicals on denominators. This is called rationalizing the denominator. So if I had something like, let's look over here, let's say the square root of 5 divided by the square root of 2. Well, I can't simplify those individually, and if I combine them, I can't simplify them together either. But I can get rid of the square root of 2 on the denominator. And to do that, I can multiply the numerator and denominator by the square root of 2. So now the numerator, square root of 2 times square root of 5, I have square root of 10. The denominator, square root of 2 times square root of 2 would be the square root of 4, which is just 2. So this radical, written in simple form, would look like this. Now, it doesn't necessarily look simpler, but we did rationalize the denominator. We got rid of that square root on the denominator, so that's considered simplified. Now back to the guided practice with example 6. Example 6 says take the 4th root of 27 times the 4th root of 3, and it wants us to simplify that expression. Well, individually, the 4th root of 27, I can't simplify. 4th root of 3, I can't simplify. But what I can do, because they're both 4th root, is I can multiply them together. 27 times 3. And what I see here, even before I multiply it together, 27 is 3 times 3 times 3. Times another 3 is 81. But notice I have 4 3's underneath the radical sign. So if I take the 4th root of that, it's just going to equal 3. And that simplifies nicely for us. Let's look at example 7. We have the cubed root of 250 divided by the cubed root of 2. Cubed root of 250, not a whole number. Cubed root of 2, not a whole number. But they are both underneath the cubed root here. So I can combine them. 250 divided by 2 is 125. And the cubed root of 125 is just 5. All right, example 8. We have the 5th root of 3/4. All right, at first we look at this, seems like there's not much we can do. 5th root of 3, not a whole number. 5th root of 4, not a whole number. 3/4, I cannot simplify. So while I can separate this out, it doesn't look like I can do much from there. But notice I do have a radical on the denominator. So I do need to get rid of that by rationalizing the denominator. Now, to take the 5th root of something, I need 5 common factors. Well, right now, 4 is 2 times 2. So I only have 2 common factors. I need 3 more of them. So to rationalize the denominator, what I can do is multiply. Now, I already have 2 of them, so I only need 3 more to get 5 of them. So I multiply by the 5th root of 2 times 2 times 2, or a 5th root of 8, and keep my fraction equivalent to what I started out with. Whatever I multiply the denominator by, I have to multiply the numerator by it as well. Now I could write that as just a 5th root of 8 is fine. So on the numerator, I have the 5th root of 3 times 8, which is 24. And there's no common 5 factors in there that I can simplify, so I'll just leave it as the 5th root of 24. On the denominator, I would have the 5th root of 5 2's, which would just be 2. And so I rationalize the denominator, and that's how we could write our answer. Now, the 24 and the 2, I can't combine those because one's underneath the 5th root, one's not. So we'll just leave our answer like that. And on to number 9. We have the cubed root of 5 plus the cubed root of 40. Now, this is addition here. In order to add these, I need to have like radicals, meaning that the index must be the same, which is the case, but also the radicand underneath must be the same as well. So, cubed root of 5, there's no way I can simplify that. But that gives me a clue. In order to be able to combine these, I need the cubed root of 5 here as well. So, I can rewrite 40 as 5 times 8. And conveniently then, I can take the cubed root of 8, leaving me with cubed root of 5 plus, now the cubed root of 8 is 2. So that would be 2 times the cubed root of 5. Now I have like radicals, and I can combine them. I have 1 cubed root of 5 plus another 2 cubed root of 5, which gives me a total of 3 cubed root of 5s. When adding like radicals like this, I always start with the smallest one and simplify it first, and then use that as a guide to what you need to simplify the larger one into. Sometimes you'll have to simplify both radicals before you can combine them. And on to number 10 for the guided practice. In this section, we're asked to simplify the expression and assume that all variables are positive. So number 10 is the cubed root of 27 times q to the 9th power. Well, remember with our properties of radicals, we can split this up into the cubed root of 27 times the cubed root of q to the 9th power. Cubed root of 27 is 3 because 3 times 3 times 3 equals 9. And the cubed root of q to the 9th power, we'll think of that as q to the 9th power and then to the 1/3 power. Power to power we multiply, and I can cross cancel here, and I get q to the 3rd power. Another way of thinking about this is that there are 3 groups of 3 q's within here, so the cubed root of that would be 1 group of 3 q's. So that simplifies to 3 times q to the 3rd power. Now on to number 11. On 11, we have the 5th root of x to the 10th power over y to the 5th power. Well, I can't combine what's underneath the radical sign, so let's split it up and do the 5th root of x to the 10th divided by the 5th root of y to the 5th. Well, let's see, this would be x to the 10th power raised to the 1/5 power, which would just be x squared, because 1/5 of 10 is just 2. And on the denominator, we'd have y to the 5th raised to the 1/5 power, which would just equal y. So I get x squared over y. So you can see we can take this divided by the index to get what power we end up with. Or another way of thinking about that is that there are 2 groups of 5x's here, and there's 1 group of 5y's here. So we have 2 groups of 5x's, 1 group of 5y's, and our answer is x squared over y. Now, I'm going to make a slight modification to this problem and show you how that would change our answer. Let's suppose that instead of y to the 5th on the bottom, let's say we had y to the 6th power. Well, if we had y to the 6th power, I still have 1 group of 5y's in there, but I end up with an extra y. So I could have this y that represents 5 of them, but then I still have an extra y underneath the 5th root. But then that gives me a radical in the denominator. So to simplify it, I need to get rid of that radical. Now the y is okay, but the fifth root of y is not. And to get rid of the fifth root of y, I would need 4 more y's to get a group of 5. I have 1, I need 4 more. So I would want to multiply that, and again, whatever I do the denominator, I have to multiply the same amount to the numerator, keep it balanced. So I would need, 4 more y's on the bottom, and 4 more y's on the top. So then, multiplying these together, I'd have the fifth root of y to the fifth power again, which would be another y, multiplied by this y would give me y squared on the denominator. And on the numerator, it looks more complicated now because I'd have x squared times the fifth root of y to the fourth. I can't combine those, I can't simplify those. But that would be how I'd want to write my answer in simplest form because I was able to get rid of the radicals on the denominator. So again, that's a little hard to read, but that would be x squared times the fifth root of y to the fourth over y squared. So it was much simpler with our original problem when we just started out with it to the fifth power. Let's look at number 12. Here we have, let's see, some like bases that we're dividing. We have x divided by x to the 1/2 power, and we have y to the 3/4 power divided by y to the 1/2 power. And then I also have 6 divided by 3. So let's start there. 6 divided by 3 is just 2. Then dividing like bases, remember we subtract the exponents. So we'd have x to the first power divided by x to the 1/2 power. 1 minus 1/2 is just 1/2. So I have x to the 1/2 power. And then I have y to the 3/4 power minus 1/2. So that's 3/4 minus 2/4. Get a common denominator. And that equals 1/4. So I have y to the 1/4 power. And that is it. I've combined everything I can. There are no radicals to get rid of on the denominator. So there's our answer. Let's look at one final example. Number 13 for the guided practice. All right, here we have 2 radicals that we want to subtract. And in order to add or subtract radicals, they need to be like radicals. Now I see in both I have a square root, but I need the same thing underneath the radical sign in order to be able to subtract them. So I'm going to start with the smaller one here, and let's simplify this. All right, square root of w to the 3rd power. Well, w to the 3rd power is w times w times w. And if I'm taking the square root, that means for every pair of common factors, I can take the square root and represent it out here. So the square root of w squared would just be w, and I'd be left with w underneath the radical sign. Now, this w that I take out when I take the square root there does need to be multiplied by this w in front. So w times w, we get w squared times that 3rd w left underneath the radical sign. Now what that tells me then with this one is I want to simplify it where I'm left with just a w underneath as well. All right, so the square root of 9 is just 3. And then w to the 5th power, so I have 5 of them. For each pair in the square root, I can take one out, and I'd be left with the 5th one underneath. So I'm taking out w, square root of w squared is w, times another w, gives me w squared, w squared outside the square root. All right, so I have 3w squared times the square root of w minus w squared times the square root of w. So I can combine the numbers in front, because those are both being multiplied by the square root of w. So if I have 3w squared minus w squared, that's 2w squared times the square root of w. And there's my answer. And that concludes section 3.2, applying properties of rational exponents. Thank you.